let's continue with our exponent rule. So I'm going to show you the notes to do a quick recap of the quotient rule, of the power rule, and then I want to move into the zero exponent rule. So let's take a look. Okay, so as a recap here with our power rule, notice we had negative 3 to the 11th y. This entire expression is raised to the fourth power. This is indicative of the power rule. So because we have one term here, we want to take that power and we want to distribute power times power. Okay, so if we distributed power times power, we were left with, notice, a negative becomes a positive. Negative raised to the fourth power is going to become positive. So we have 3 to the fourth power, x to the 11th, x to the 44th power, and y to the fourth. And then we took it a step further, and we saw that 3 to the fourth power is the same as 81. 3 times 3 times 3 times 3. Notice for number 3, what we ended up having to do here is we wanted to use a different strategy, and that is to apply the order of operations first. By applying the order of operations first, we simplified inside the set of parentheses to start the problem. And notice in yesterday's class, I rewrote the contents of that set of parentheses. I simplified the set of parentheses, which resulted in a 1 to the first power, a b to the ninth, over a 9 to the first, and a c to the eighth. I put the parentheses back, I brought the negative back in front, and I raised it to the 10th power. So all I did was I rewrote the problem, but with the simplified version of what was inside the set of parentheses. At this point, we had the power rule, so we took our power on the outside and we multiplied by each of the powers inside. Again, because this is one whole term. If we had multiple terms within the set of parentheses, we need to take a completely different approach. Okay, so we multiplied power times power throughout each of these separate bases with their respective powers, and that led us to a negative 1 to the 10th, b to the 90th, over 9 to the 10th, c to the 80th. And then, of course, 1 to the 10th is simply 1. The negative stays because that 10 is not being applied to that negative. Recall that it was in front of the set of parentheses. And then when we punched in 9 to the 10th, we noticed that was insanely, massively huge, so we left it in exponential form. Okay. Let's get into the zero exponent rule. The zero exponent rule is super awesome. It states that any base raised to the 0th power is 1 except for 0. So one thing I wanted to comment on first is that x to the 0 is equal to 1, right? X, the base, is being raised to the 0th power, so x to the 0 is 1. Now, recall here that g to the 0th is not the same as g to the first. So I really want you to be super careful. I have seen students say, oh, if we have g to the 0, isn't that the same as g to the first power because it becomes a 1? No, 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 no. If that were the case, then why would they be different numbers, right? That doesn't make sense. It does not make sense for g to the 0 to be the same as g to the first. So be super careful. G to the 0 is simply 1. Okay? So let's look at a bunch of quick examples. We have d to the 0. Okay, d is being raised to the 0. There's no other bases. There's no signs. So this entire quantity is simply equal to 1. Negative 5 quantity raised to the 0. Notice the entire contents are being raised to the 0th power. So, okay, that's equal to 1. 2 to the 0, same thing. We have a numerical base this time, but that doesn't change the fact that when you have a base raised to the 0th power, it's simply 1. Okay, that works out. Notice with part D, we have m times d to the 0th power. Every base has its own power. So this is actually m to the first times d to the 0th. Well, if you have m to the first, and you're telling me that d to the 0 is 1, see, we even wrote it above it, d to the 0 is 1, then m to the first times 1 is simply m to the first. For part E, notice the 0 is only being applied to the base 49. This is that idea of parentheses versus no parentheses. This is why I have them stacked, so you can see the difference. The 0 here in part B is being applied to the entire contents in -5, hence the set of parentheses. With part E, that 0 is only being applied to the 49. So 49 raised to the 0th power is 1, but don't forget there's a negative in front. So your answer here would be -1. And last, with part F, we have 5 to the 0. Well, 5 to the 0 is just 1. M to the third, that's okay. N to the 0, well, that's another 1. So 1 times m to the third times 1 is simply m to the third. And we're done. That's how we apply the zero exponent rule. So what we're going to do for the next couple problems is we're going to combine a few rules to make sure that we're understanding this. Okay, number 1, we have a negative on the outside of the set of parentheses. Okay, very cool. Inside we have 4x to the 5th, y to the 0, and this entire quantity is being raised to the 10th power. Recall that if you have the opportunity, you really should simplify within the set of parentheses just to make life a little bit easier. So notice here we have a y to the 0th power, and you know that that becomes a 1. So if we rewrite this, 4x to the 5th times 1, do you agree that 4x to the 5th times 1 is simply 4x to the 5th? We want to simplify inside the set of parentheses. So we want to be clear about applying the p in PEMDAS in the order of operations. So let's just rewrite this. Negative 4 to the 1st power, right? The base, every base has a power. X to the 5th power, and this entire expression being raised to the 10th power. Notice here I just said 4 times x to the 5th times 1 is simply 4x to the 5th. But I'm going to write here that my power for 4 is, my base 4 is a 1. Now that I've simplified inside the set of parentheses by applying the zero exponent rule, I'm now going to apply the power rule. We know we are applying the power rule because the 10 on the outside of the set of parentheses, we're going to distribute power times power, power times power. The negative in front of the set of parentheses is going to stay because it is not impacted by that power of 10. If the negative were inside the set of parentheses, that's a different story. So we have 4 to the 10th power and then x to the 50th power. 4 to the 10th power is pretty massive, so I'm just going to leave that in exponential form, and voila, we're done. Moving on. Let's take a look at the next problem. Okay, we have 9m to the 8th, n to the 0th power, all over 3m to the 2nd, n, raised to the 3rd power. Let's write PEMDAS again. Okay. Notice I would like to simplify what's inside the set of parentheses first. It's going to make life easy. We're going to change things up and just simply move from left to right. So 9 over 3. Notice here we have a 9 in the numerator divided by 3. Well, we all know that 9 divided by 3 is 3. And obviously the 3 is going to be left in the numerator because it's larger. So let's simplify. That becomes a 3. M to the 8th over m squared. Here we are going to apply the quotient rule. So m to the 8th over m squared, you subtract the powers. 8 minus 2 is 6. It's heavier in the numerator, so we have m to the 6th by applying the quotient rule. And I'm going to make a note here that we're applying the quotient rule. Then we have an n to the 0. N to the 0 is simply 1. So if n to the 0 is 1, then 1 times anything else is everything else. So it's an identity, which means it does not change what's inside that set of parentheses. I could write times 1, but we know 3m to the 6 times 1 is 3m to the 6, so I'm going to leave that there. And then notice we have an n in the denominator. I took care of my numerical bases. 9 divided by 3 is 3. I took care of my m's. M to the 8th divided by m to the 2nd is keep the base, subtract the power, so m to the 6th. And then when I got rid of this n to the 0 and turned it into 1, I still have that n in the denominator. So I'm not allowed to just move it up. That's not cool. You're not supposed to move bases unless they have a negative exponent, and I'll show you that in a second. So we're going to keep the n in the denominator exactly where it's located. Notice the entire expression is being raised to the third power. So the first thing we do is we take care of what's inside the set of parentheses. And we did that successfully. Now, every base inside the set of parentheses has a power. So this is 3 to the first, m to the sixth, n to the third. At this point, we're ready to apply the power rule. Power times power. So let's distribute power times power, power times power, power times power. That gives us 3 to the third, m to the 18th, all over n to the third. I would urge you to be analytical about your numerical bases. In this case, we have a 3 to the third power. 3 times 3 is 9 times 3 is 27. No big deal. Let's evaluate that. So we have an answer of 27, m to the 18th over n to the third. And now we're officially done with this problem. Okay? So again, some good strategy to apply to these kinds of problems is to simplify inside the set of parentheses and then go from there. All right, let's take a look at the negative exponent rule. What I've done over the years is I wanted to help you guys have a quick and straightforward way of simplifying the negative exponents without overthinking this. Okay, so notice here the definition. We have x to the negative m is the same as 1 over x to the positive m. That's an interesting concept. So x to the negative m, this term is in a numerator, right? Because we can simply write this over 1. But when we simplify this expression, this x to the negative m, it ends up moving to the denominator, and the power becomes positive. That is very interesting. What did not happen is that these flipped position. That is not what happened. And I'll show you a bunch of examples that proves that. Let's take a look at this again. We have 1 over x to the negative m. Well, if your base with a negative power is in the denominator, well then we're going to move it to the numerator and raise it to a positive power. So what I've written here is steps for you to use while you simplify expressions that have negative exponents. So what I found that's helpful is to first circle the base and its a negative exponent. So for instance, in this case, we would circle the x to the negative m. Move the base from the numerator to denominator, or vice versa, depending on its location. So notice here, my x to the negative m is in the numerator. So I'm going to draw an arrow that shows, oh, we're going to have to move it to the denominator. When we move it to the denominator, we raise it to the positive power. So we change the power from negative to positive. Similarly, with our second example, x to the negative m is in the denominator. So we're going to move it to the numerator. When we move it to the numerator, we raise it to the positive power. Not overthinking this, let me show you your expressions here. So we have negative 2 over y to the negative fifth. Okay, circle the base and it's a negative exponent. So we have a y to the negative fifth power. Okay, now notice it's located in the denominator. So we are going to take that and we're going to bring it to the numerator. When we bring that expression to the numerator, that base to the numerator, its power then becomes positive. So my answer is negative 2 y to the fifth. Notice that the negative 2 stays. I don't do anything to that negative 2. The negative 2 does not have a negative exponent, so it stays exactly where it's located, unless we had a reason to simplify it. In this case, we simply don't. Okay? With our examples and on your tests and anything, you're never going to leave any negative exponents. So you want to make sure that you clean that up. Let's take a look at part B. Carefully, let's dissect this. We have a negative 3 to the negative 2, x to the fourth, y to the negative 8. Okay, for a fact, we know that y is being raised to the negative 8th power. Okay, that's a good one. For a fact, we know that 3 is being raised to a negative 2, not negative 3. Remember the difference between using parentheses versus not using parentheses. So I'm going to circle the base being raised to the negative power. Perfect. The bases being raised to a negative power are 3 and y. So both of these will move into the denominator. Notice I still have a negative and I still have an x to the fourth. So we can leave this in the numerator. My 3 to the negative 2 and my y to the negative 8, they're both going to move to the denominator, and we're going to change their powers from negative to positive. At this point, just like our previous problem, 3 to the third is 3 times 3 times 3, which is 27. 3 to the second is 3 times 3, which is 9. So we're going to rewrite our answer as a negative x to the fourth, and then 3 squared is 9, and then we have a y to the 8th. And then we're done. Remember, the negative here is not a negative exponent. So there's no reason to apply the negative exponent to a negative quantity, okay? Only apply this rule when you have a negative exponent. Let's do it again for part C. In part C, we have 4 to the negative first power. I'm going to circle it. We have m to the negative third power. I'm going to circle that. And then we have 4 to the negative third power. I'm going to circle that guy. Okay. Notice that the 4 to the negative 1 and the m to the negative third, because they both have negative powers, these are both going to move to the denominator. So here's my fraction bar. I'm going to write 4 to the first power in the denominator and m to the third power in the denominator. Notice this 4 to the negative third power is in the denominator, so I'm going to move it to the numerator with a positive power. But then, you notice how there's an m to the ninth in the denominator? It stays. We would only move it if it has a negative exponent, and it does not. Now that we've applied the negative exponent rule, we notice a couple things. We have the same base here, but one's in the numerator, one's in the denominator. So that screams quotient rule. And then we have the same base here, but they're both in the denominator. So m to the third times m to the ninth, well, that screams product rule. So we are going to apply 3 different exponent rules to this one problem. We already applied the negative exponent rule. Now we're going to apply the power rule. If you have 4 to the third over 4 to the first, you keep the base, subtract the powers. So 3 minus 1 is 2. It's going to be left in the numerator because that's where it's heaviest. That's the quotient rule. Now we're going to apply the product rule. M to the third times m to the ninth. The product rule stated, keep the base, add the powers. And that leaves us with m to the 12th. Now think about this again. We have 4 to the second power. Well, 4 times 4 is 16. So let's finish this problem off by evaluating. All right, let's take a look. Each base is being raised to a negative power, so that's pretty interesting. So just like we stated in our steps to help us simplify, we're going to circle the base and its negative exponent. So that's the first one. We notice that it's going to end up moving to the denominator because they're all in a numerator. You'll know where they're located if you have, excuse me, if you have a fraction and they're in their specified location. Like for instance, this 2 is definitely in a numerator. This y to the negative 5 is definitely in a denominator, right? It's a fraction, so you know where they're located. X to the negative third, also same situation. Y to the negative second, also same situation. Now you're probably thinking to yourself, okay, these are all going to move into the denominator, right? So if they all move into the denominator, what in the heck is in the numerator? Well, Bethany, you are absolutely correct. And Josh, nice job. If everything moves to the denominator, so 2 to the fourth, x to the third, y to the second power, well, wouldn't it suffice to say that you need a placeholder in your numerator, and that is definitely not going to be a 0? Because 0 divided by anything is 0, so why would you put a 0? Instead, you would recall that it would be a 1. So your final answer, notice, is going to be 1 over, and then take a look, 2 to the fourth. 2 times 2 times 2 times 2, well, that's easy. Now we have 1 over 16, x to the third, y to the second. Nice job, Bethany and Josh. That was perfect. Beautiful. Let's turn the page and keep going. That was excellent. Okay. 5 to the negative 2, m to the fourth, n to the first. M to the negative over m to the negative 8, n to the second power. So what we're going to do with this problem here is we're going to simplify it. We're going to make sure that we don't leave any negative exponents, and we're also going to identify the exponent rules used. I am going to do this one with you right now in class. You are going to take these two home. Okay, Christine, when you move a base from a numerator to a denominator, that power goes from negative to positive, or vice versa. I'm just going to show you really quickly. The fact of moving the base from the numerator to a denominator, or vice versa, will change the power from negative to positive. Keep that in mind. Anytime you take a base with a negative power and you move it, it just becomes a positive exponent. Okay, good. So let's take a look at number 1. I want to walk you through number 1 slowly, and I want you guys to do number 2 and 3 at home. I would like you to send me an email with the image of your work for both of these. I don't want just the answer. I want you to show me the work. Okay, let's take a look at number 1. The first thing we notice is that we have negative exponents. So we're going to use the negative exponent rule. Taking this slowly, we are going to circle every base with a negative power. So we've got 5 to the negative 2. That's currently in the numerator. So we know that we're going to move it to the denominator. When we move it to the denominator, that power becomes positive. Okay, we're just going to keep that in mind. We're going to continue to scan, and notice that we have an m to the negative 8 in our denominator. So we want to circle that guy. And then we notice, okay, well, I want to make sure that my exponents are positive, so I'm going to move m to the negative 8th to the numerator. So let's rewrite it first. In the numerator of my fraction, I have m to the fourth. The m to the negative 8 moves up as a positive 8, so m to the 8th. And we also have an n to the first power up top. Take a look. M to the fourth, n to the first, cool. M to the negative 8, well, that moved up, and now it's m to the positive 8. This 5 to the negative 2 was in the numerator, but we've got to move it down. When we move it down to the denominator, it becomes 5 to the positive 2. And notice in our denominator, we still have that n squared. So we're taking this nice and slow and being critical about where everything is located. That takes care of negative exponent rule. Now I notice that I have m's, which are the same base, right next to each other. So if I read this out loud, it would read m to the fourth times m to the 8th. Oh, well, that's the product rule. According to the product rule, you're going to keep the base, add the powers. Okay, so keep the base, add the powers. Keep plus powers. Hopefully that abbreviation is fine for you. So m to the fourth times m to the 8th, we are going to keep the base and add the powers. 4 plus 8, that's 12. Next, we also notice we have common bases, but one's in the numerator, one's in the denominator. So specifically, this states n to the first divided by n squared. Well, we know that that's definitely the quotient rule. So according to the quotient rule, we keep the base and subtract the powers. But remember, we're going to leave it where it's heaviest. So we have 2 minus 1 is 1, and it's heavier in the denominator, so we're going to leave it down there. 2 minus 1 is 1. And so the first power will be left in the denominator. And then we do have 5 squared. We know what 5 squared is. 5 times 5 is 25. And we have just completed that problem. I am looking for the exact same thing from all of you. I would like you to answer 2 and 3. And in that answer, I would like you to identify the exponent rules. In order to get full credit, I need to see which rules you ended up using for each of these problems. Okay? So these are for homework. Make sure you email that to me by Monday. So I'm going to say email by Monday. This guy and this guy. Cool. Let's take a look at this interesting piece here. So we have 2g to the, that's a question mark, by the way. That's an unknown. So 2g to the question mark, h to the negative fourth, this entire thing being raised to the negative third power. Okay. What I want you to notice really quickly is we could do a couple things. We could take this h to the negative fourth and bring it to the denominator, rewrite this, then distribute the negative 3. We could. Or I'm going to show you what your options are. Now, what this is saying is it wants us to identify what that exponent should be, because it's a question mark right now, so it's unknown. What we do know is that our resulting answer is going to be h to the 12th over 8g to the 6th. So we definitely know that somehow, whatever we plug in here, we've got to get a 6 out of this, right? So we have a question mark. We have a negative 3 on the outside. This is interesting. So what I'm going to do is I'm just going to rewrite what we have here. So 2g to the, I don't know, h to the negative fourth, all of this being raised to the negative 3. I am going to push you to play around with a couple of ideas. So the first thing is we could bring the h to the negative fourth, circle it, bring it to the denominator, and rewrite it as a fraction, correct? Or we can notice that each base has its own power, a 1, a question mark, a negative 4, and this negative 3 is on the outside. So wouldn't it make sense that it's the power rule, power times power? So let's take a look at it. I just want to see what this looks like. If I do that, that gives me 2 to the 1 times the negative 3 is a negative 3. Question mark times negative 3. Can you just say that that's negative 3 question mark, because it's negative 3 times the question mark? So it's almost like a variable, right? Like if that were an x, you'd say negative 3 times x or negative 3x. And then we have negative 4 times a negative 3, which is 12. So interestingly enough, what's happening here is that we notice, okay, well, this is going to come down. And we also notice that we have a g to the negative 3 question mark. This entire expression is also going to come down. So let me rewrite this for you. In my numerator, I have an h to the 12th. In the denominator, I have a 2 to the 3rd. And by the way, do you see that 2 to the 3rd is 8? 2 times 2 times 2 is 8. Interesting. And then we're going to bring down the g to the negative 3 question mark, and that becomes 3 question mark. Now notice we want this expression to be equal to h to the 12th over 8g to the 6th. Well, now it becomes a piece of cake. What number does that question mark have to be in order for this to be 6? Well, you guessed it. Cece, you were so close. That question mark has to be 2. 3 times 2 is 6. So that question mark has to be 2. So my answer for this guy is 2. I would like you to also play around with number 2 in the same fashion. Give that a shot. See what you guys come up with. Have fun with it. What I'd like you to do is continue to apply the rules that you've learned and just see what you can come up with. Okay? I'm looking for these 3. All right, guys, let's keep going. Nice job, Cece. All right, we are ready to multiply polynomials. I made a note here that a monomial times a monomial is one term, right? So think of a monomial as what you know, it's one term. Another monomial, one term. So do you agree that 1 times 1 is 1? If you're multiplying monomials, you should get a monomial. So number 1 is similar to what we've seen already. The first thing we notice is we have a negative 3, then we have an x to the 5th, then we have a y to the 4th. We have a 7, then we have an x to the 11th, then a y to the 2nd power. This is actually the product rule. When we applied the product rule, we liked starting with our bases first, so I'm cool with doing that again. So let's start with the x to the 5th and the x to the 11th. X to the 5th times x to the 11th is keep the base, add the powers. Y to the 4th times y to the 2nd is keep the base, add the powers. And then look at the fact that we have a negative 3 times a 7. Okay, negative 21. We're done. Don't overthink it. Finish. Notice we have a monomial. It is one term. We know if we have more than one term if we see addition or subtraction, like number 2. If we take a monomial, which is one term, and we multiply it by a binomial, which is 2 terms, 1 times 2 is 2. So after we distribute, we should have 2 terms. So let's take a look. Notice for number 2, we are going to distribute the negative 5m squared because we know that this says negative 5m squared times 11m to the 3rd minus 8m to the 2nd. All right. Let's start here with our first pair. A negative 5 times 11 is a negative 55. And an m to the 2nd times m to the 3rd, keep the base, add the powers. That is going to be m to the 5th. Awesome. Next, we're going to distribute the negative 5m to the 2nd times a negative 8m to the 2nd. A negative 5 times a negative 8 is a positive 40. And an m to the 2nd times m to the 2nd is keep the base, add the powers. All right. As a reminder, we are using the product rule. Keep the base, add the powers. Good. Let's do it again. We have a monomial outside the set of parentheses, and we have a binomial inside. So let's multiply. First things first, we have a negative 4 times a 1. There's a 1 in front of this x cubed y, so negative 4 times 1 is negative 4. X to the 1st power times x to the 3rd power is keep the base, add the powers. So it's x to the 4th. Then we have a y squared times y to the 1st power, keep the base, add the powers. So that's y to the 3rd. There's your first term. Now we're going to distribute the negative 4xy squared to the 2x to the 5th. Same exact idea. Negative 4 times a positive 2 is a negative 8. X to the 1st times x to the 5th is keep the base, add the powers. But then notice we also have a y squared. No big deal. All right, let's see how you guys did. As a reminder, the coefficient here is a 1. If it helps, you can write it in there. You can always write your coefficients of 1 wherever you please. So we are going to distribute monomial times binomial. So 1 times 6 is 6. M to the 1st times m to the 5th is keep the base, add the powers. That's m to the 6th. n to the second times n to the fifth, well, that's keep the base, add the powers, n to the seventh. Beautiful. Now we're going to distribute the 1m to the first, n to the second times a positive 1m to the first, n to the first. I love it, Josh. I love it. 1 times 1 is 1. M to the first times m to the first is m to the second power, right? Keep the base, add the powers, 1 plus 1. N to the second times n to the first is n to the third. Keep the base, add the powers, 2 plus 1. And you're done. That's it. Beautiful, right? That's why I love this section. It's so fun. It's just like, oh yeah, let's just put it all together. Let's expand on this idea. So we took a monomial, we multiplied by a binomial. We noticed that 1 times 2 is 2, so we were left with binomials. Each expression, we had binomials. I love it. But what happens when we have a binomial times a binomial? Reasonably speaking, if a binomial is 2 terms and another one's also 2 terms, well then 2 times 2 should be 4 terms, right? So we will get 4 terms. What that doesn't say is whether or not we can actually combine like terms afterwards. But I want to prove to you, you will have 4 terms. Okay. What I want you to consider is how to distribute for a binomial times a binomial. Notice that when we had 1 term in front of the set of parentheses, we would distribute to everything inside the second set of parentheses, right? We're going to do that same idea, but we're going to first distribute the 2x alone, and then we're going to distribute the 3y. So what I'd like you to consider is that anything in the first parentheses, each term in the first parentheses, you have to distribute to everything in the third one. This applies even if you have a 3 by 3, a trinomial times a trinomial, or a binomial times a trinomial. It always applies. First term, distribute through the second parentheses. Next term, distribute through the second parentheses. If you had another one, you distribute through the second parentheses. Don't overthink it. All right, let's do the math. We start with a 2x times an x. Remember, these are both powers of 1. So 2 times 1 is 2. X to the first times x to the first, keep the base, add the powers. Next, we take the 2x times a negative 11y. 2 times a negative 11 is a negative 22. But then we have an x times a y. Well, that's just x, y. Cool, no big deal. They're not common bases, so you can't add them. Next, we're going to move to the 3y. We finished with the 2x because we distributed to all terms inside the second set of parentheses. So we're done with the 2x. Next, we move to the 3y. So 3y times x, well, that's the same as 3yx, but I want to write it in the same order. So this is going to be plus 3xy, alphabetical order. And last but not least, we have 3y times a negative 11y. Well, 3 times a negative 11, that's a negative 33. And then y times y, or y to the first times y to the first, is keep the base, add the powers. 1, 2, 3, 4 terms. Exactly what we expected. Now, notice something very interesting. We have an x squared term. We don't have any other x squareds. We have a y squared term. We don't have any other y squared. But we have 2 terms that both have xy. Guess what? These are like terms. So if we combine these 2 terms, a negative 22xy plus 3xy, well, negative 22 plus 3, isn't that a negative 19? So my final answer becomes, and I'm going to make a note that these are the same, become 2x squared minus 19xy minus 33y squared. We only combine the like terms that we can, and we did it. Let's do it again. Also, do you notice it's kind of like a rainbow or some sort of smile? It's nice, right? It's kind of feels good. At least I think so. It's a nice problem. So we are going to distribute here. We've got the 5b. Let's distribute to both terms in the second set of parentheses. Once we finish distributing that 5b to everything in the second set of parentheses, we're then going to distribute the 3c. I find that by drawing the lines of distribution, we tend to have better success. It keeps things organized and neat. So I would urge you to do that. You don't have to do it, but I would urge you to do that. 5b times 4b, well, that's 20b squared, right? And again, think about how it sounds. B times b, well, you have two of them, so b squared. 5b times 3c, that's 15bc. 3c times 4b, that's 12bc. And then 3c times 3c is 9c squared. One of the errors I typically see is that when students multiply b times b, they forget to square it. Or when you multiply c times c, you forget to square it. Just be logical about it. It does not make sense for you to say b times b is b. That doesn't make sense. B times b cannot possibly stay b. All right? So think about that logically. Next, let's combine like terms. These two are alike. So we have 20b squared. 15 plus 12, well, that's 27. So 27bc plus 9c squared. I hope you're loving this because I love this section. I think it's so fun, and I feel like it's such a great way to just throw myself into math and feel really good about it because you know that you have such a successful outcome. Like generally speaking, students get these right all the time, and I love it, with the exception of, you know, the one or two students who forget to square. But that's it. It's really fun. Look at number 7. You cannot apply the power rule here. Okay, I know that you see that there's a power on the outside. This is 4m minus 7 raised to the second power. So you're thinking, can't I just square each of these? No, no, no. You must rewrite the polynomial first. You must rewrite the polynomial first. So 4m minus 7 to the second power is actually 4m minus 7 times 4m minus 7. You have to rewrite it first. I'm going to prove to you why that is. So first off, 4m minus 7 to the second power, you already know means you have to take the 4m minus 7 and you multiply it by the 4m minus 7. What you might have thought is, hey, can I take a shortcut and just square the 4m and just square the 7? Well, I'm going to do the math this way, and I want to prove to you how you lose a term by simply skipping a step and trying to just square it. It doesn't work, and I'm going to prove to you why. We are going to draw our lines of distribution, right? Pretty sweet. 4m times 4m, that's 16m squared. 4m times a negative 7 is negative 28m. Negative 7 times 4m is negative 28m. And negative 7 times a negative 7 is positive 49. These, ladies and gentlemen, are not opposites. They do not cancel each other out. They do not go away. They have the same sign, so you must combine them. We will end up with 16m squared minus 56m plus 49. Now imagine if you had said, oh, I'm just going to take a shortcut and I'm going to square the 4m and I'm going to square the 7. If you square the 4m, sure, you've got the 16m squared. If you square the negative 7, sure, you've got a positive 49. But what you missed is your middle term. So be super careful. Anytime you have a binomial, trinomial, 4-term polynomial, whatever it is, anytime you have a larger than a monomial being raised to a power, You must rewrite it that many times, and then you must distribute. Okay? I'm going to do one last problem with you guys, and then I have to let you go. We didn't finish today, and that's okay. Let's do this last problem. We have two binomials. Let's distribute. 9b times 9b, well, that's 80. Wow, I said b. Those are p's. 9p times 9p is 81p squared. Cool. 9p times negative 4 is a negative 36p. Awesome. 4 times 9p is a positive 36p. Super cool. And then 4 times a negative 4 is a negative 16. 4 terms. I love it. But check this out. Now what do you notice? These are opposites. A negative 36p and a positive 36p, they'll cancel each other out. So the answer to this particular expression is 81p squared minus 16. Awesome. Nice job, guys. On that note, I've got to let you guys go. We've taken up all the time we have for today. On Monday's class, we'll quickly finish this unit. It's going to be so fast. Make sure you have your factory notes handy. We are going to move into Unit 7 on Monday. All right? I hope you guys enjoyed that. I think it's fun. I hope you guys were like, yeah, this is cool. This is definitely manageable. I'm going to be in my office hour at 11 in 10 minutes, so come join me. All right, guys? If you have questions, come join me. Don't hesitate to ask. Don't be afraid to ask